All right, we're going to introduce the concepts of moments and torques. Now, the term moment is actually more of a mathematically derived term. The practical thing, you never hear somebody talk about the moment output from a car. It's more the torque that's coming off of a motor. All right, so the more classical, the more relevant engineering term I would use would be torque. The more classically British and more mathematical expression would be moment. They mean the same thing, okay? And I will use those terms interchangeably, quite frankly. This comes quite naturally. So I want you to take a look here. I've got a... this is basically, consider this to be like a valve control. So here this is the horizontal plane, point A, and I have a 2 meter long, this would be really long, valve lever coming off. All right, and right here at the end, there's a 100 Newton force being applied. And what is that force trying to do? Well, it's quite obvious. It's trying to take this lever and twist it counterclockwise. All right, so a torque is an effort or moment to rotate something if it could. Now, it may not be able to rotate that. Why? Well, maybe there's a lot of friction. Okay, so you can have rotational friction, so as you try to rotate that, there's something grabbing on this thing and basically giving an opposition to it, like static friction. Same idea. So this is making an effort to cause rotation. May not be successful. That's okay. All right. So we're having a moment or a torque due to this force. All right. And let's just, common sense tells us if that moment arm were longer out here, so the force was applied here, the effect of the moment would be, or the torque would be greater. There would be a greater effort basically being applied at this point to rotate right there. The larger the moment or the torque, the more, and that it is happening essentially at this point. All of this moment or torque is trying to make this thing rotate about this spot. Okay? So, and as that were to rotate, okay, we would have our rotation, we would count as being in the Z, coming out of that little hub right there. Okay? So let's see. So there's two factors. How far are you away from where you're trying to make rotation happen? And then how big is the force associated with this effort? So when we have a moment or a torque, the units are going to be composed of something with the force and something with the distance. All right. Now the magnitude of this torque, and I'll just say moment magnitude, is, in this case, 200 Newton meters. 100 times the 2 meter moment arm right there. Okay, and the direction is in the Z. Okay, it's wanting to take this thing counterclockwise. If we use our right hand, okay, the thumb points up in the, let's bring this down. My thumb is pointing up, that's in the Z direction. My fingers are cupped in the counterclockwise direction. Okay? Now, we can express this through cross products. So, I want you to note that 200 Newton meters in the Z is equal to 2x cross 100y. Okay, x cross y gives z, and 2 and 100, 200. Okay, so it's important to note here, when we were looking at velocity, that was omega cross r. Okay, but when we're looking at moments, or torques again, that is R cross F. It's reversed, okay? Not F cross R. Big lightning bolt coming down. No. All right? So, and again, so we have a 200 Newton meter torque being applied counterclockwise. If this thing moves, so be it. If it doesn't move, it's telling you there's a torque being applied in the clockwise direction to prevent it. All right? Basically, if you have no motion, the sum of all the torques or moments will be 0. All right? If this doesn't move, if this doesn't rotate, it's because another torque is arising to oppose it. If there are no other torques, that thing's going to start rotating. Okay? Now, so there's that basic idea. Let's consider the same thing, except now I'm going to let this moment arm go up at an angle, and we're going to say that's 45 degrees. Whether it is or not is not important. And so here's our 100 Newton force, and this is still 2 meters. So if we look at this, we can just look at that and go, oh, 2 meters this way, 100. It's still going to want to rotate. So this still corresponds to a torque as a vector being 200 Newton meters Z. Okay? But I would note, we could have done this. This is just looking at this way, or we could have done it more formally. The torque is 2, so we got to do the R cross F. So if we go from here to there, we'd have 2.707x plus 0.707y cross 100 newtons, the force, and this would be minus 0.707x plus 0.707y. And if you do all the cross products, you'd wind up with the same thing. Okay? I'll leave that to you to do. But here's the point I want to get across. If R and F are perpendicular, we don't need to do the cross product. We can just take R times F, note whether it's positive or negative Z, which will correspond to clockwise, and we can write down the answer immediately. This is important. The moment arm and relative to the force, all that matters relative to this force is perpendicular distance. Given a force, what is the perpendicular distance to get to here? All right, so let's take a look at this from another perspective. Kind of start bringing this home. So, same idea. This is again supposed to be at 45 degrees, 2 meters. But now suppose the force is just horizontal. So here's the force coming in here. What's the torque? Well, it's going to be less. Now, let's just note here. Okay, so if I was to look at where I could bring this force along here. So if I was to take this force, slide it this way, and check this distance, that would be 2 sine 45. Or I could just pull that off right in here. So it looks to me like the perpendicular distance to get to here, all right, this is all that matters, this distance, or taken right there. So I think the torque should wind up being 2 times 0.707. That would give me this distance times 100 newtons Z. Well, does the math check out? Yes, it does. So we have moment, 2.707x plus 0.707y cross 100 minus 100y. This is going the negative y direction. All right, so let's see what we have here. So here's the force. And this is what I have here. Oops, I did that wrong. Minus 100x. Okay, so here's the force, which is in the x. It's not the y is going up, obviously. And here's the, from this term, we get perpendicular distance. All right. This distance along the x we don't care about. Why? We wind up because we get an x cross an x that gives 0. So in the end, we're left with y cross x is negative z, but that negative here changes it to a positive z, and we're left with 2.707 100 Newton meter. Oops, left the m off here. Z. So here's what we're seeing. Relative to a force, all that matters is the perpendicular distance associated with where the point of rotation is going to be originating from, right there. Okay? And we can take this a little bit farther. And giving my nature, I will do that. So what I want to do is, let's consider a point O, and we'll let A come off of it. Here's the point A, and we'll let a force occur at A. So I'm going to let ROA is 3x plus 4y. So I got 3 here, 4 there, the usual coordinate system. And F, applied at A, is 10x minus 10y. I'll put a little Newton on there. Okay, so we have a x component of force, y component of force. Now, if we did this by pure vectors, all right, so then the moment about O would be 3x plus 4y cross 10x minus 10y. Okay? Now, you evaluate this by just this cross all of this and y cross all of this. But when you go to cross this with that, the 3x and the 10x, well, that gives 0. So all we're left with is x cross y gives z, but we got a negative sign, so I've got a minus 30z coming off of this term. And then y cross z gives a y cross x gives a negative z, so I got a minus 40z, so I got a minus 70 z Newton meters equals my moment about O. All right, so notice all that matters is this 3x goes with that 10y, and this 4y goes with this 10x. So if I had the x component of the force here, Fx only has to match that 4. The y component of the force, all that matters is the x component of the distance. Okay? So all that matters relative to a force is perpendicular distance, and to that extent we can break a force down into its x component and match it up with the y distance, and the y component of the force with the x distance. And then we just have to note, is everything clockwise or counterclockwise? If it's counterclockwise, it's positive. If it's clockwise, it's negative. Now, I'm going to take this 1 point further. All right, so suppose I have a point A out in space. All right, and I have some arbitrary point B here. Okay, and at B, I'm just going to draw this slightly off here for a reason. I have a force. Now this force has a direction, so I'm just going to note it's the direction of that. Just make this line right in here. Okay? So if I wanted to get the moment of this force about A, I would then go R from A to B cross the force. Well, rather than use x and y, what if we were to simply come in and do something like this? This is perpendicular. And so I'll let this distance here, I'll call this my little x. So I normally have capital X and capital Y. So this is sort of a script x. Okay. And I'll let that be the origin. And I'll let script y go off this way. So if I did that, I would then have some little amount a, and I'll call this some little amount b. So I would have a along the x plus b along the y cross f, which is actually along my y-axis. And what do you notice? Rather than using this xy, just using this more oriented one, I wind up with the moment is a, f, z. Okay? Counterclockwise. That makes sense. But notice something here. This b cross the force, which is along this y-axis, that gives 0. So what does that tell us? When you have a point where you care about the moment or torque, and you have a force, look what I can do. Along the line of the force, I can move that force right back to here. Yeah, it's applied at B, but so what? I'm going to move it back to this point. And look what happens. As long as I move it on that same line of the force, because this distance B is irrelevant, in the cross product, you get y cross y, it's gone. That force can be anywhere along this line, and I compute the exact same torque. Doesn't matter. So what that shows you is that you could be having forces applied to a body. Maybe that's not the most convenient place. Just visualize sliding it along the line of the force to a more convenient place where you can just pluck off the perpendicular distance. So you got A times F, boom, you got your torque. You're all said and done. So this is kind of neat. You can move forces along their line of application anywhere, and the torque equation will not change. The result will be the same. Move it where it's convenient for computation, and go with it. All right. We will continue taking this further in our next video. Catch you then.